Today we discuss section 5.4 reduced residue system and the Euler-Fermat theorem. So first we have a definition of reduced residue system. By a reduced residue system, modulo M, we mean that any set of phi of M integers incongruent modulo M, each of which is relatively prime to M. For example, we take M is equal to 8. We have 1 cap, 2 cap, etc. 8 cap are residue classes modulo M. Here M is equal to 8. Then if we choose one of the representatives from each of these residue classes, say 1, from this I'll take 10 and 3, 4, 5, instead of 5 I have taken 13, 6, 7, 8. Okay, this comes from residue class 1 and this comes from residue class 2, because the remainder of 10 when it is divided by 8 is 2, so we can say that this 10 belongs to this residue class 2. Then 3, 4, 13 comes from the residue class of 5, because the remainder of 13 when it is divided by 8 is 5, and 6, 7, 8. So this form a complete residue system. So this is what we called complete residue system. So if we choose some of the elements like I'll take some 9 and 3, and I'll take 13, then 7. This constitute a reduced residue system, because this 9 is relatively prime to 8, 3 is relatively prime to 8, 13 is relatively prime to 8, 7 is also relatively prime to 8, and these are all incongruent modulo 8. We know that phi of 8 is always 4, so we can say that this contains exactly phi of 8 elements, all are incongruent modulo 8. So this form a reduced residue system. So we have taken a reduced residue system as a subset of a complete residue system. So this is the meaning of the definition. Now we have a theorem 5.16. If A1, A2, etc. A phi of M is a reduced residue system modulo M, and if GCD of K comma M is equal to 1, then the set Ka1, Ka2, etc. Ka phi of M is also a reduced residue system modulo M. Now we have proof. In order to prove this set is a reduced residue system, we will first prove that these are all incongruent modulo M, and each of these values K1, K2, etc. are relatively prime to M. If Kai is congruent to Kaj mod M, implies M should divide K times Ai minus Aj. That implies M divides Ai minus Aj. Since the GCD of K comma M is equal to 1, we have this divisibility. From this you can write Ai is congruent to Aj mod M. So this is a contradiction, because this form a reduced residue system. Therefore, all these elements are incongruent modulo M. So we can say that Ki congruent to Kaj are also incongruent modulo M. Now we will prove that each Kai is coprime to M. For that we assume the GCD of this is equal to D. Then if we need to prove that D is equal to 1, if otherwise D is greater than 1, there exists a prime P which divides D. Okay, so From this you can write D divides KAI, comma D divides M. That implies since P is the prime divisor, then P divides the same KAI and P divides M. That implies P divides KAI implies P divides K, or and we have P divides M from this, or we have P divides AI and P divides M. This implies P divides GCD of K comma M, or P divides GCD of AI comma M. This implies P divides 1 or P divides 1, because GCD of K comma M is equal to 1, or we have GCD of AI comma M is also 1, then we have P divides 1. So this is a contradiction. So there is no such P. So that means D greater than 1 is not possible. Then consequently we have KAI comma M is always equal to 1. So this shows that these elements KI's are all in congruent modulo M, as well as this KI's are co-prime to M, and it contains exactly 5 of M elements. Then by definition we can say that this is also a reduced residue system. As a consequence of the previous theorem, you can prove theorem 5.17, Euler's-Fermat theorem. Now we have the statement. Assume GCD of A comma M is equal to 1. Then we are all familiar with the statement. A raised to phi of M is congruent to 1 mod M. So one possible question is to state and prove Euler's-Fermat theorem. Now we can prove this theorem. For that we assume B1, B2, etc. B phi M be a reduced residue system. That means all these elements are in congruent modulo. From this you can get two conditions. Bi's are incongruent modulo M, and these Bi's are coprime to M. That means GCD of Bi comma M is equal to 1. This is the definition of a reduced residue system. So we start with a reduced residue system. Then we have the set AB1, AB2, etc. AB phi of M is again a reduced residue system. This is what we have proved in the previous theorem. So we know that this is also a reduced residue system. But we know that if you consider this M, then we can get from 1 onwards, I'll write this 1, etc., etc. M minus 1 cap are the complete residue system or complete residue classes. Among these classes, we will choose representatives in such a way that these are all relatively prime to M. So if we choose from this, you can choose 1 and etc. M minus 1 numbers which are relatively prime to or co-prime to M. We can say that this form a complete reduced residue system. Now our assumption is this is a reduced residue system. So instead of this we can choose exactly these numbers. Okay, instead of B1 you can take 1, and instead of B2 we can take the other number which is coprime to M, and so on. So instead of this B1, B2, etc., B phi of M, we can take this as well. Okay, or since this is again a reduced residue system, we can say that this AB1 comes from one of these residue classes. Clear? Therefore, then we can say that AB2 comes from this AB1 need not be comes from this one residue class of 1, but in some other residue classes, because we have multiplied this B1 with A. Similarly, AB2 come from another residue class from this collection. So we can say that AB1, if you divide this AB1 with M, you can get a remainder which is in this set. So we have b1 into b2 etc. b5 of m. These b1, b2, etc. b5 of m can be replaced by these numbers. This is congruent to a b1, a b2, etc. a b5 of m mod m, because the remainder when b1 is divided by m is r1, we can say that the same remainder will be obtained from one of these numbers. Okay, because one of these numbers comes from the residue class of b1 itself. Okay, then some of these numbers comes from the residue class of b2 itself. So we can write it as a b1, a b2, etc. These numbers. Then we have b1 into b2 etc. into b5 of m is congruent to a raised to 5 of m, again b1, b2, etc. b5 of m mod m. Now you can use the cancellation law. Since b1 comma m is gcd b1 comma m is 1, we can cancel this b1 from both sides. If we cancel these two numbers, this modulo can be replaced by m by gcd of those numbers. M by gcd of those numbers is gcd of bi comma m, that is always 1. So you need not change this modulus because of uh, this reason. b1 and m are relatively prime, so gcd is 1. So using the b2, we can cancel b2 from both sides. Since b2 gcd of b2 comma m is equal to 1, you can get the same modulo m. Cancel up to this b5 of m. Then we have 1 is congruent to a raised to 5 of m. 1 is congruent to a raised to 5 of m mod m. This is what we called Euler-Fermat theorem. Now we have two interesting consequences of this. That is obtained by putting m is equal to p a prime. If m is a prime, then this can be translated as a raised to 5 of p congruent to 1 mod p. That implies a raised to p minus 1, since phi of p is p minus 1, this is congruent to 1 mod p. Okay. This is actually we can consider this as a corollary of this Euler-Fermat theorem. Then what is the meaning of this? For any prime number p, we have p divides a raised to p minus 1 minus 1. Okay, so from this you can write, this implies a raised to p minus 1 minus 1 is equal to some k times p. Then when we multiply it with a, again we can get a raised to p minus a is again kap is a multiple of p again. So from this you can write p divides a raised to p minus a. That is p divides a raised to p minus a holds if this Euler-Fermat theorem holds. Euler-Fermat theorem holds if a comma m is gcd a comma m is equal to 1. So this holds if gcd of p comma a is equal to 1. Okay, that means p does not divides a. If p divides a, you have a is equal to multiple of p, implies a raised to p is equal to multiple of p, implies a raised to p minus a is also multiple of p. Consequently, p divides a raised to p minus a, implies in both cases a raised to p minus a is congruent to 0 mod p. So these are the two important consequences of Euler-Fermat theorem. So these two consequences are termed as theorem 5.18 and 5.19. Now we have theorem 5.20. Okay, and in theorem 20 we have if a comma m is equal to 1, we know that ax congruent to b mod m has a unique solution. If this is the case, Then using this Euler's or Fermat theorem, we can get the exact solution of this equation, okay, this congruence relation. That is, if we let x equal to b a raised to phi of m minus 1, we can get this x is the solution of this, okay, because if we replace this x by this number b a power phi of m minus 1, you can get this is equal to uh, b a raised to phi of m, but we know that this is congruent to mod m because a raised to phi of m is congruent to m. So we have a instead of x, we have this is congruent to 1 mod m. So we can easily, this is a rule to find the solution of the linear congruence. Ax congruent to b mod m has a solution if a comma m is equal to 1. Then that solution can be obtained using this formula. X is equal to b to the power b times a to the power phi of m minus 1. So as a consequence of Euler-Fermat theorem, you can get this is the solution of this linear congruence. Using linear congruence, you can get in this case a comma m is equal to 1, then this has exactly one solution. If the GCD of a comma m is equal to d, we have exactly d solutions that we have proved in the earlier theorems. So we will get that solutions, d solutions, using the solution of one such linear congruence. Okay, so this is this completely classify the solution of linear congruences. So we can conclude section 5.4 by classifying the solutions of all linear congruences, even though all linear congruences do not possess solutions as well. In this section, there is one solved example is there, so we need to go through the example, and next lecture we will discuss section 5.6.